Hello, coming back to the next week. So again late, but I'm here. So the first what we shall deal with is how to use the Riemann integration, which is the same as the Newton integration for big class of functions, to measure things. And the first thing to measure is the length on the real line. That's easy because what you can imagine is we've got the real line, so that's this. And then on the real line we shall have some set, right? The set can be just a lot of points or spots, right? So could be parts of integrals or intervals, etc. And the easy way how to do it is just to measure such a set A via an integral, which will be an integral from -infinity to infinity. And what we shall integrate is the so-called indicator function. So that will be this thing. And the indicator function is just this one. So you see, so it's 1 in the points where the points belong to A and 0 elsewhere. So integrating this will simply tell us how big the set A is. And now the problem is whether the integral exists, right? So for many sets it won't. For example, if you take a unit interval, say this one, 0, 1, and I will take the set A, which is below 0 and 1, but only A will be equal to 0, 1 intersection with Q. So clearly for such a set, the upper integral of phi will be 1, the lower integral of phi will be 0, right? Because in each small interval you will also you will always have a representative with value 1, that will be one of the rational numbers there, and you will also have a representative with value 0, because that will be a irrational number there, and they are always there. So that's how we define the measurable sets. Unfortunately, although it's nice that the Riemann integration is finitely additive in the domains, so if we have disjoint union of pieces like A, which are finitely many only, then we can just say that it works. So this measurability concept is well defined for finite splitting of our sets. So if we split our set into finite many pieces and question whether the whole set is integrable, then it will be measurable, then it will be exactly if and if each of the parts is. But it's unfortunately not sigma additive, in the sense that countable many splittings will work as well, because it doesn't, right? So not countably additive. So, and usually the people say sigma additive instead. So that's a big drawback of Riemann integration. We shall come back soon. But what about lengths in more general setup? So of course we would like to see that we can also measure things in higher dimensions. So for example, if we have a plane, so we can have a curve there. So how long is the curve? Or we can have a three-dimensional thing and we shall have a curve there. How long is this curve? And that's not that difficult to think about, because the curve CT will be just having 3 coordinates, or as many coordinates as we have got. So it will be a vector valued thing. So n in the pictures is 2 or 3. And then of course, if we want to see at the level of differentials how big the linear approximation of the length is, then it must be the square root of C1 dash T square plus and so on Cn dash T square, right? And therefore obviously the length if we parameterize the curve from time, say, a to times b, then the length will be integral of from a to b from this ds, which is integral from a to b of the square root, so I will not write it again, dt. Right, so so that's very easy, and this way we can compute how long a circle is and see the amazing thing, or verify the amazing thing that the circle, so if you draw a circle in a plane with radius r, you know that the length of the curve will be 2πr, and the mystery in that is that it's linear in the radius. That's the important thing, right? And this can be computed easily, and there is some number pi, so what? So that's a constant, right? But the point is that the constant is valid for all the diameters. Right, so that's about the lengths. And what now about the areas and volumes? So this is more tricky. Here we are a little bit cheating, right? Because actually what we would like to do, if we define, say, area in a plane, so if we have got a plane and we would have a set like this there, then we should like to do something similar as we did with measuring the length in the real line, right? So we should like to make something like a grid and look for the inner and outer measure, in the sense that we shall take something like a upper and lower estimate of how big the sum of the small circles, not circles, squares is, which cover it or which are inside, and that will be again the Riemann integration, right? So there will be again Riemann integration in Rn. We shall come to that later. So that's not what we are dealing with now. But what we can do is, for example, if we have a function from a and b, and we want to continue how big is the area below the graph, then this is exactly how we motivated the definition of the Riemann integral. And we shall see later that these two concepts coincide. So here we simply define the area of a shape in plane, which we can bound by graphs of functions. So of course, if it's something more complicated, if it would be something like, say, this, so then we would have to choose some line and coordinates so that the upper part and the lower part are bounded by a graph, which is the case now, and we compute them one by one. First this one, then this one, and then we add it together. Right, so this is how we compute the areas in plane using the Riemann integral. And similarly, we can also compute volumes, but it works only for special cases. So the one discussed here as a typical example, classically always done, is the rotational of things. So you have a graph of a function, so say something like this, and what I do is I let the graph rotate. So I think there will be one more axis z here, so that's x, y, and z, and then what I get is the rotational thing. Oh, what happened? No, this way. Right, so you have the rotational object, and now we can compute both the surface. Again, it's important to understand how the differential of the surface, the area would look like in terms of the original graph. And that's easy to see because we shall imagine that what we are dealing with is simply pieces like this. So this will be the dx, and here will be the circle of radius y, which is the value of our function, right? So we know how much it will be. If we compute the volume, then it corresponds to the area of the circle, and we know how the circle is big. So this is the formula which you can read here. So this is of course the formula then for the volume, because you see it's PR square. So you go from A to B and you add this sort of small pieces of cake of the radius fx, and that's it. If you want to compute the area, so the surface, so of course it's just this, because that's the length of the small piece of the curve. So you simply have to take the length of this small piece of the curve, that's this, and that's how you get it. So you see, there is nothing complicated in that, and we can stop here and go for the next presentation about what I call differential equations soon.